say stuff. Heavenly Father, we thank you for this day. Help us to use this time wisely. Help me to say things which are correct and not complete gibberish. Amen. All right. I'm a little bit tired. Anybody want a Starburst? Say I played the what's it called? What is it called? Little League when I was little for a time. They used to have the best candy. You get candy for like 25 cents or whatever. But they had a lot of like little things and nerds and all the rest of it. It was great. And then your higher end stuff like, snow cones or. All right. I probably should get this down because you guys probably might have questions about the test, right? Should I show you the test? Seems slightly unfair, but.
Just open the test on your computer on the TV. You didn't show it to us. It's just
Let's see here. If I can find it. So you guys have questions? Go ahead and ask away.
Can we discuss the orbit stabilizer theorem?
Discuss the orbit stabilizer theorem, you say?
Yes.
Sure.
It's not in our book, but it is in your old minutes. We have orbit decomposition theorem.
Orbit decomposition theorem, I think, is what I meant. Yeah.
So it's not, like you did talk about orbit stabilizer in class.
Right.
Using your notes, your old notes.
Mm-hmm.
And so you meant orbit decomposition yesterday?
Well, the orbit. Let me find the words.
Decomposition's on 367.
There we go. Yes, I meant for you guys to be able to prove the orbit decomposition theorem. So, of course, we have, let's say, star. What does it do? It takes in a pair of things, G, and you want me to use S or X? It doesn't mean whatever for the set. S, all right. I think the book uses X, but whatever. And then, so this is the group action. What does it mean? That means that star, G star, star is annoying. G dot X is an element of S, right? For all G and G and X in the set, right? Two axioms. What are the two axioms we need? Number one, we need that when the group identity X on X, you go nowhere. Number two, you need that sort of associativity condition, that A times B times X is the same as AB acting on X, right? These are the two axioms of a group action. Yep. No, this is the definition of a group action. I mean, I think you need to know, I think you have to understand this in order to understand the orbit decomposition theorem. I'm working there. I'll get there. So that's a group action. Then we study a couple of important things, right? The one thing is, I call it G sub x. The book calls it S of x, right? It's the stabilizer. This is a subgroup of the group, right? So this is G and G, such that G dot x is what? Well, it's x again, right? So this is a subgroup of G. That's the one thing we talk about. The other thing we talk about is the orbit. The orbit of x, which I like the book's notation for this, actually. He says that that's G dot x. So that's his notation for the set of all things which the group action reaches when acting on x. All right? This is not a group, but what it is a subset. It's a subset of S, right? So the orbit decomposition theorem has a couple pieces. It also involves something called the fixer, right? Well, not the fixed subset, rather. X sub f, the fixed subset. What's this? What's that? Well, maybe. I think that's the fixer. I don't find myself using the fixer in anything except for that homework problem. Sorry. They can't all be winners. Let's see here. So this would be x and s, all right, such that, all right, G dot x is equal to x for all G and G. Let me put this into words. The fixed subset, in other words, it's the set of all points in S whose orbits are what? So we have what? We have basically G dot x is equal to what? X, but that's a, see, here's the thing. You say it's x, I say it's the set containing x. It does matter, but it is the set containing x because the orbits are sets. Otherwise, I couldn't say that the orbits partition S, right? So that's like the next step in this thought process. So we've got this group action, we've got orbits, but and then the thing is the orbits, if we look at the set S, right? If we look at the set S, then there's these fixed points, right? There's these things that are in here, right? The things that the group acts on and goes nowhere. There's those things, right? And then there's the interesting things. Maybe this whole upper corner is like one of them, and then there's this piece and that piece and that piece. But these are the non-singleton orbits, let's say. You can prove that the group action defines an equivalence relation on the set, right? What is it? We could say x is equivalent to y if and only if what? If and only if they have they're in the same orbit. This would be equivalent to saying if and only if, you can say y is equal to g acting on x for some g. this, if you actually try to prove something about the equivalence, I think this formulation is probably more convenient to you, right? Saying that the sets are equal. I think that's conceptually helpful, right? Two points are equivalent if they're in the same orbit. But if I actually want to prove that's an equivalence relation, I want something easier to work with. Logically, I think that the squiggled underline. I mean, how do you show that any point is equivalent to itself? That's axiom 1, right? 1 times x is equal to x again, right? So x is equivalent to itself. X is this reflexive property. How about symmetric? I think I did this in class one day. If I have this, right, then if I act by G inverse, right, use axiom 2, use axiom 1, well, use definition of group, and then axiom 1. So check it out. If y is related to x, then x is related to y. So that's a symmetric property. And you could prove transitive much the same. So the orbits are the equivalence classes with respect to this notion of equivalence, right? That means they partition the set. So, and that essentially brings us to the orbit decomposition theorem, because the orbit decomposition theorem says what? It says that the size of the set, right? This is for a finite. I think it's for finite S, right? I mean, I suppose it's probably, yeah, like group act on a finite set. That's probably kind of important. It's hard to count if we're dealing with infinity, right? It's a little bit, we'll leave that to Sprano. So, I mean, that's kind of his specialty. Let's see here. So the size of set, right? It's equal to a sum over the partitions, right? Afforded to this, right? That's a very vague thing I just wrote. Let's be more specific. It's equal to the size of everything that's in an orbit unto itself, right? These things. And then plus what? Plus the size of the orbit of, let's say, x sub I equals 1 to n, where the orbits of x1, the orbits of x2, these are the what? I think you guys just told me. Yeah, non-singleton orbits. Now this is still not the orbit stabilizer theorem, is it? Because there's one missing piece that I haven't put out here yet, have I? If when you look at the equation on page 368, it doesn't have just the size of the orbits, does it? We've replaced that with what? Right, so this is instead the index of the stabilizer. This is, I think, proved in the lemma or lemma 2 possibly, that the size of that the index, the number of right cosets of the stabilizer, although I think the proof is for left, is the cardinality of the orbit. And the proof of that involves building an explicit bijection from the orbits to the set of cosets. Wasn't a particularly difficult proof, but I'd actually have to think about it, so I better not.
And the orbit stabilizer theorem uses that same thing, pretty much.
Yeah, so this is the orbit decomposition theorem, right? Orbit decomposition theorem, which is what I meant to say yesterday. I'm sorry, guys. I should have said orbit decomposition theorem.
And this notation is S of x sub I the same as like R G sub x?
Oh, I'm sorry. I was just looking at the book. But you're right. In my current lingo, I should really say that, shouldn't I? Yes. Thank you. So let's get back to my example from the old notes, right? What's the orbit stabilizer theorem?
The order of G equals the order of, yes, the order of G equals the order of the orbit
Huh. Let's see here. Let's see here. What if the action's transitive? So what it means for an action to be transitive, and it's not something we've emphasized in here, is that the orbit of any point, right, gets you everywhere else. So like the action's transitive if this is not interesting in some sense, right? There's just a single orbit. You have class.
I know, it's not stupid. And it's my one class that takes attendance.
I'm sorry.
I know.
I'm trying to remember. I think what if there's just one orbit, right? So the size of the orbit of any point you like, x, right? What if that's equal to the number of things in the set as which being acted, right? Then that would be this would be equal to the index, right, of G and the stabilizer of x, right? But by group theory, this would also be the size of the group divided by the size of the stabilizer. And I think that's the orbit stabilizer theorem, which says that the size of the group, right, is equal to the size of the stabilizer times the number of things which are being acted on. Yeah, there it is. That's the orbit stabilizer theorem. Yeah. So that's a special case of this when the action's transitive. That's a very good question. Man, I should have made that a question.
You're saying it's not.
There's still time.
Do we have to have that?
So, for example, we figured out that.
It's just the French theorem and the fact that,
Yeah. Exactly. It's the.
the x is equal to the orbit.
Right. Yeah. In special case, this is transitive. I guess it doesn't. Yeah. So when we apply this to the cube, right, if we look at S being the set of faces, then you look at the stabilizer of one face, we figured out we had D4, right? So there was 8 things in there, and so 8 times 6 was 48. And then I got confused because I thought it was 24, but that's because I'm only allowing for rotations. I'm not allowing for the isometries which flip the cube inside out. Those are actually, in some sense, they're not motions of the cube in the sense that those can't be realized in regular three-dimensional space without actually ripping the cube apart and putting it back together by flipping sides over. Right. It could be realized as a motion in 4 dimensions, but that's harder to see. It's easier to see these things for a triangle, right? The motions of a triangle in the plane are just rotations, right? But if you can take the triangle and you can lift it out of the plane and turn it over, that gives you another isometry, which is not a motion in the plane. But in 3 dimensions, you can actually visualize that motion, right? Same with the cube, it's just harder to see. I shut up about that. That's a good question. Anyone, one more? Anybody? Okay. You guys got other questions? I'm going to try to end here at 5:50 because I got to go grab something before I go home. And then apparently it's going to take me a half hour to get to my house when I enter the neighborhood because of the trick-or-treaters. I've been warned. I'll just go fast. I figure they'll move. The kids got to learn sometime, right? No?
Why they're learning what we read about, I assume.
My philosophy of calculus instruction and driving home on Halloween. Let's see, weed out the losers. No, wait a minute, no. It seems wrong. It seems wrong. Now I'm going to have to edit this. Great, great, great. Maybe not. One thing I don't think I made the connection explicitly enough, the correspondence theorem in chapter 8, where we had that really nice homework problem about, that we talked about here in the help session last week, that is the lattice isomorphism theorem that I talked about earlier. So like, oh goodness, if I can draw a picture of it. What did we look at? Was it D? Oh man, was it D4? Was that example? The homework problem we worked, was it D4? Looking at subgroups of D4 as they, like we looked at, I think we looked at, I'll say D4 mod K, right? So K was the center of D4, which is in fact the set 1A squared, right? So, and then D4, of course, is 1A, A squared, A cubed, B, BA, BA squared, BA cubed, usual song and dance for A and B. All right, so the subgroup diagram of this is what? So like, what is D4 mod K? You got K, of course, right? You got yourself a KA, right? Yeah, you got yourself KB and Kaba. Yeah, very good. And that's it, because KBA cubed, for example, well, KBA squared is equal to KA squared B is equal to KB, because A squared gets absorbed into K because A squared is in K. And likewise, the KBA cubed is not anything new, because that's KAB, which is, why did I do that? I don't know why I did that. There must have been a reason.
It's in KPA.
Yeah, because A squared is
Yeah.
Oh, this is equal to KBA? Okay, I'm sorry. I'm just having trouble. Seeing that at the moment. Whatever. So you got these four things, right? And so this has three subgroups, namely the one generated by Kaba, Kub, right? And of course the subgroup generated by Ka, right? And then below all these, you just have the stupid subgroup for the factor group, right? These are subgroups of the factor group. The correspondence theorem says those correspond to intermediate subgroups between K. Like over here in the real group, there's K down here, right? And it says that there is intermediate, I called them H1, H2, and H3, right? So this in the book, I think he's like curly H1, curly H2, curly H3. So correspondence theorem says that there's this interplay between those two. And then what else is there in D4? There's other subgroups of D4 beyond. Those are four element subgroups, right? Like this H1 is what? You could look you could kind of look at it as k comma ka, right? This one you could look at as k comma kb to just use a, this is, I mean, this is, I should put some quotes around this because it ain't quite right. So to be more explicit, I mean, this is useful to me as a mnemonic to remember it, but that's 1a squared, a cubed, a to the, I forgot my a. I did 1a squared and then a cubed, there we go. And over here, you got 1a squared b and a squared b, which is ba squared. And this one, of course, 1a squared ba and ba cubed. Right? I mean, that is what the correspondence theorem says, is you literally just expand those over in the original group. It gives you corresponding intermediate subgroups. So, I mean, these are subgroups. So you have k less than or equal to these, less than or equal to me, subgroup of H, subgroup of, in this case, D4. The question is, you know, what kind of intermediate groups between a normal subgroup and what are the intermediate subgroups between a normal subgroup and the total group? Well, you can find what those are by looking at subgroups of the factor group is the point. But the way I looked at this before was in terms of like the lattice diagram of the whole group, right? So like my perspective before was to focus on the lattice diagram of the whole group. What is the lattice diagram of all D4? I mean, apparently, you've got these 4-element sets, right? Let me just, I hate so much writing. We call this H3, H2, H1, right? These. What else is there, though? So let's see here. There's the center, right? Which is 1a squared. And of course, these are above that in the subgroup diagram. You said also what? 1 and b. Where does that fit? Is 1b a subgroup of H2? Ah, it is, but it's not what? But K is, yeah. Oh man, my picture's not helpful, is it? So, because I find myself wanting to do something horrible like, which is almost certainly a bad idea in terms of picturing things, right? But you're right, that's a subgroup of H2. Just like H3 has subgroup what? What, 1BA? Is it 1BA or is it, yeah, 1BA. And H1 has subgroup. This is horrible.
No, I don't think.
H1 has nothing?
Well, it has K, but I think that's it.
Oh, okay, okay.
So H2 would also have 1BA squared.
H2 would have 1, is BA squared, 1BA squared a thing? Oh, wait a minute. I don't know, I'm not going to be successful in doing this correctly. But, let me just, I'm sorry, this is not helpful to you guys, and I'm not quite with it enough to do it properly here. Let me look it up for you guys. Because I had these to look at earlier, right? I mean, I had a...
Yeah, I think that you have them on your notes.
You know, I had something I made for you guys this semester specifically. Maybe it was it in the old, I don't think it was the old notes on this one. come on, where'd that go? We looked at it together in the projector, and it was like
It had like a double line.
yeah.
Oh, was it a website?
Was it lecture 18? Ah, here it is. No, duh. I still have some personal demons I'm battling in terms of writing, like drawing decent pictures of subgroups. So the subgroup lattice, like, I have problems. We'll just say that. Come on, I got no laser. Come on, man. So, let's see here. This is from Dummett and Foote, and the top one, maybe I think this one's more fun. So here, of course, the center is also, we could just say it's generated by a squared, right? A squared is the generator, so R is like RA. And so that's a normal subgroup, and so these are actually the subgroups of dA, which correspond to the factor groups of D8 by the center, by the R squared generated group. And in terms of generators and relations, it's actually a little bit even easier to kind of see, I guess. That's a good question. I do not remember what is the terms and condition of the dihedral group in Dummett and Foote. That might be our D4.
I mean, it kind of looks like
But, yeah, if it is, I guess that's what I was trying to create, right?
yeah, because it has two from like our H2 and our H3.
So this would be our
So,
The middle one is our H1.
H1.
no.
Oh, that's our H1.
Yeah.
This is just A, so
Okay.
and then the second one is squared. S B comma A squared.
So this is the ka. And this is the kaba, and this is just the kub. And let's see here, below each one of them, so there's three, that's interesting, there's an asymmetry between the Ka group versus the Kb and the Kba. Like the Kb, this one, it's got this, and that as subgroups in the original group, and likewise for this one. But the K, just Ka, it only has the center as a subgroup. It's interesting. There's a, and so you can see why my attempt to draw a picture was all messed up, because I should have put the H1 in the middle, not on. See, putting it on the side made me get everything all twisted. Anyway, the interesting thing here, I suppose, is that, I mean, one way to look at this is if you can find and understand the factor group for a normal subgroup, you can find intermediate subgroups even though you only have a partial knowledge of the full lattice diagram, right? Like we could find those H1, H2, and H3 not knowing about all this, right?
So in the QA example, is the K the -1?
Yeah, -1 is the center, which is the set 1 minus 1. That's the center of the quaternion 8 group, which I also call the quaternion 8 group. And yeah, I guess that right there you're looking at is the full lattice diagram of subgroups for Q8. And so you can see the lattice diagram for the factor group of Q8 by -1 by the double lines. So the way I stated it before, it was most useful if you're given, right? If you're given the lattice diagram for a group, you can take that and easily construct the corresponding lattice diagram for the quotient, right? But the homework problem that we worked last week is more about starting with the quotient and going back the other way and gaining information about the subgroups which exist in the original group by studying the factor group. So it goes both ways. That's correspondence theorems of bijection, right? That theta map. It goes both ways. Here's the, oh, I think this is literally, this is it. Yeah, okay, so, yeah, duh. But on the other hand, you notice that this is also slightly misleading because what he should emphasize is that this is not the lattice diagram for G. It is what? Yeah, it's just the part of the lattice which appears above the normal subgroup. But there's more, right? There's these two things and then, right? Yeah. Right, that's what, yeah, exactly. That's the double line part of the total diagram in the way of thumb and foot notation. Yeah. Anyway, other questions? If you have a question, I'll at least listen to it. Anybody want to start first? First bounce. I got the red one. I got the pink one. Take the red one. All right. Red or pink? Pink. All right. Sorry, it's kind of fun. I should always bring these to class. It's rather enjoyable. I do need to bring Daniel back. Yeah. I need like a starburst gun, something like that. You know. That is true. Next time they come to me telling me, "Do you have any projects for us to do?" and I always tell them things, and they always say things like, "I don't think that's legal," and I'm like, "Nevertheless, I want it." Like, you know, I want something that'll open all the doors into Moss or things like that, you know. Yeah, so I should ask them for it. I need a starburst gun. And of course, I'm sure that you will find a reason to use the 3D printer to do something on it, even if it doesn't really need it. But so. What's that? Made it out of Legos. Ooh. Yes. Yeah. We good? Okay. All right. Well, call it a day then. Now I got to just